All right, welcome back. Hope you had a good break. So I've said this before, the Wednesday schedule is going to be a little weird. So a lot of it, if your desire is to come here and take the exam, normal class time, normal length of time, you can do it. All right, I will start an exam in here at 12:45 on Wednesday. If you want to start a little later, I'll have that option. And if you're in my lab section, there'll be an option. You'll get instructions for that as well. So Wednesday, you'll have sort of your choice of when to come and when to do. I will be available for a review session, which will be a lot like this class, but maybe you work some more stuff on Tuesday night in Salem 12. That's the big room on the ground floor, the lowest floor. I shouldn't say the ground floor. If you come in from the library, that is the first floor of Salem, but it's the middle of 3 floors, right? So if you come in from Winston Hall, or the side, if you come in ground level on the side, you're on the bottom floor. Salem 12 is on the bottom floor. I'll hang around after class for an office hour. I'll have some office hours tomorrow published. And then I'll have some availability next week. So our final is a week from Wednesday, which is a mind-blowing event. I will have more to say, but I'll probably say it on Canvas about the final. Briefly, the final is cumulative over the three exams, right? So you don't have time to go like learn organic chemistry 2. If you don't know organic chemistry 2 at this point, like if you don't have any foundation, if you walked in off the street, yeah, I haven't seen you all semester, you're in trouble. What you should do with your 3-hour exam. So exam 3, I'm going to basically sit down. I will not be available on Thursday. I'm going to sit down and try to bang that out and have it back to you. Like I'll try to have it back to you as soon as I can with a key. And what you should do with your 3 midterms is go through them carefully. Like maybe rework the blanks. The blanks are all going to be online. Rework the blanks, see what you remember. Like if you reliably know acid-base chemistry and you don't know, I don't know, chapter 18, focus on 18, right? You really at this point, some of this needs to be in your head pretty solid. You want to patch holes. A lot of you I've talked to were sort of right there. And just need to get over that last hump. So kind of use the hour exams, the midterms, to identify where the hump is that you got to get over. What else? I'm going to try to come up with an alternative time for the final. I don't have one right now, right? So it has to make sense. I'm not going to give an alternative final on Tuesday or Thursday. That's one day different. But if I can find a room on Monday, I will. If I can find a room on Friday, I will. If you have 3, we are not allowed to give you. I shouldn't say we're not allowed. The university promises you relief if you have 3 exams in a 24-hour period. So if you do have that, talk to me. Like some of us have to give. You don't get to just dictate terms at that point, but the 3 professors giving those exams need to talk to each other and figure something out. I'd say if I don't hear from you about that by exam 3 on Wednesday, I'm going to assume you're okay. Office hour tomorrow. Yeah, I'll have that. You should have at this point. I'll go in and try to find. You should be able to see on Canvas an online evaluation form for me and the class. So you get to evaluate both of those things. You can evaluate them independently. You can say that you could, for instance, say you love organic chemistry, you hate my guts. Vice versa, you hate us all, you love us all. Like all things are on the table. If you're wondering what I look for, I do look at them, but I obviously don't get to see them until I assign grades. And to be honest, I usually don't look at them before I go away for the holiday. And when I say go away for the holiday, I mean, stop. I put the class out of my mind for a little while. But if something really worked, if something didn't really work, you know, I care less if you think I'm great or do you think I suck. Like, I'm not saying I don't care about it, but like, if that's all you say, I'm great, I suck, I don't learn anything from that. So if you have something that could make the class be better, that would be fun. All right. So, like, as I promised, I have no new material. My idea is you've been working some problems and would have some questions at this point. I'll take those. I'll probably answer fairly verbosely. Or other questions?
For Gabriel synthesis, when you use hydrazine, how do you get the vibe?
Yeah, I didn't really go into that because so there's two things. I had 3 emails about the Gabriel synthesis. I guess that's something I went through fast that then the book devotes. I think I generate a lot of questions when I either go into a lot of detail about something the book is short on or vice versa. Like if I don't talk much about it, it does. So the Gabriel synthesis historically was like the first big advent in how we synthesize primary amines, right? So you can't, this goes back to, you remember, if I want to make, I don't know, if I want to make methylamine, right? I take ammonia and methyl bromide. Ammonia displaces that. That looks like that synthesis would work. And industrially, they actually do it like this. I said I would answer this verbosely. Industrially, they do it like this. Okay. So then the problem is, right? Ammonia can take this proton. Proton exchange, and then over alkylation. So if you just take ammonia or a primary amine and you start trying to alkylate it, the problem is the amines are bases, proton transfers can happen, and you can over-alkylate the amine. So if you want methylamine, you end up getting methylamine and dimethylamine and trimethylamine and even tetramethylamine. Industrially, this works out. You can just take ammonia and mix it up with methyl bromide, and you get all 4. Like if I'm trying to sell chemicals to the world, which there are a lot of companies that do this, and if you do this on a large enough scale, then you know you can invest in a enormous distillation stack, and you can separate those 4 amines, and you can sell all 4 of them. But in the lab, like if you think about the lab you've been doing all semester, right? Like that, in a lot of ways, that's not very similar to what we do as organic chemists. In a lot of ways, it is. That's the scale we tend to work on, right? We try to make a gram. We try to make 50 milligrams to 10 grams. That's the common scale to work in an academic lab setting. All right. In an industrial scale where you're making tons and tons of material, you can invest in the separation and it makes financial sense. So on the small scale, the Gabriel synthesis was the first way humans found to avoid this problem. So if we go through that, I always love it when they leave markers out that don't work. Right, so in the Gabriel synthesis, you start with dilimide. You treat this with potassium hydroxide. Right, that H sits on an electronegative atom between 2 electron withdrawing groups. This gives us a nitrogen anion. That nitrogen anion is quite nucleophilic. So now but it's only nucleophilic once. Right, so it reacts, you get that nitrogen attached to some kind of compound, some kind of alkyl group. And then that nitrogen, right, this lone pair is delocalized over both carbonyls, so it's not very nucleophilic. Amide nitrogens aren't basic or nucleophilic. So that nitrogen stops, it doesn't overreact. Overreact being a technical term. Now, finally, 20 minutes later, he answers the question. So there are sort of two ways to take care of this. One is alkaline hydrolysis. And honestly, this is the way I've done. I mean, I've done this exactly one time in my life. This is the way I did it. I used potassium hydroxide. Potassium hydroxide is cheap. It's in every lab everywhere. So aqueous potassium hydroxide, reflux this. What does reflux mean again? Condense. What's the temperature of my water at this point? What's the boiling point of water? 100 degrees, right? Reflux means you're boiling it. Reflux, when you reflux something, and again, this is the way organic chemists or reaction chemists tend to select temperature. Water boils at 100 degrees. So rather than try to like engineer some apparatus that will hold this reaction at 97 degrees, let's say I wanted to do a reaction at 97. Instead of doing that, I just say I'm going to do it at 100. I'm going to put it in water. I'm going to boil it. That will guarantee the reaction's at 100 degrees. And like as long as there's water in there boiling, remember your high school chemistry, physics is if you've got a liquid and a solid, or if you've got phases at equilibrium, they have to be at either the melting or the boiling. So I can apply a ton of heat. As long as there's water in there to boil, it will stay at 100 degrees. The way we, if you think about that, if you do this at home, if I say I want to boil my pasta for an hour, I can't just, put a little bit of water in a pan and go away because the water all boils out. We put a reflux condenser on it. The water boils, it hits the condenser, it falls back down into the solution, and I have a constant amount of water. It stays at 100 degrees. All right, so this would give us, first to me, I have not. I'll do that. So we just get an aqueous hydrolysis or an alkaline hydrolysis of the amide bonds here, right? Hydroxide attacks, pick electrons up, pick electrons down, pick a nitrogen out. We get a dianion. This dicarboxylate is water soluble. We separate that easily from the organic amine. Off we go. If I were you doing a Gabriel synthesis, this is how I would do it. You can also use hydrazine. Question. Hydrazine is that. NH2 bonded to NH2. And we're going to wind up with this byproduct. Right? That byproduct is not soluble in organic alcohol like ethanol. So if you do this reaction in ethanol, the byproduct falls out of solution. Your question was how do we get that? All right. The way we get that, like hydroxide over here attacks the carbonyl. The same thing happens with this nitrogen. That nitrogen attacks the carbonyl. We kick electrons up. Get a tetrahedral intermediate. We shift some electrons around. We kick electrons down. Nitrogen comes out. Right, you guys aren't allowed to do that on the mechanism. Right, so this nitrogen is now an amide nitrogen, not very nucleophilic. That's why we brought along a second nitrogen. That nitrogen is not. This one does the same thing. The nucleophilic nitrogen hits the electrophilic carbonyl carbon, pop electrons up. Tetrahedral intermediate, moves some protons around. O minus kicks out the NH2 here. And we get this product, we get that product.
But the protons move with the saltness.
Yeah.
Can you also do it with H3O plus?
You could, yeah. Yeah, so if you do that, the question was here, can you do a hydrolysis with H3O plus? And you can. So we can hydrolyze any carboxylic acid derivative to the carboxylic acid with H3O plus and water. And so aqueous acid will hydrolyze a carboxylic acid derivative to that carboxylic acid. Hi. Aqueous base will hydrolyze a carboxylic acid derivative to the carboxylate. Right, so that's the big difference here. We use KOH, the acids we're going to get are going to be O minuses. Again, keep track of the pKa's. I have, we've talked a lot about acid-base chemistry since exam 2. And the chemistry, you need to pay attention to that. So if I do H3O plus here, so if I use your route H3O plus, that means going to come out to be CH3 NH3 plus. Right? If I have an amine under acidic conditions, so if the pH of the solution is lower, more acidic than the pKa of the base, it's going to be protonated. So definitely pay attention to, we talked about that in exam 2. As you review, you should definitely be thinking about that. But pay attention to, are the conditions alkaline or the conditions acidic? That was the answer to your question was buried in there somewhere. So another reason we don't use, if you think about the other, the way I would recommend doing this whole thing, I would use azide and CH3 bromide, right? Because N3 is accomplishing the same thing, and it's what we call more atom efficient. If you think about the atoms you start with, and how many of those atoms end up in your product, the Gabriel synthesis is actually used, if you take intermediate organic chemistry, Chem 321, or any of the graduate level organic synthesis classes. This is sort of an example of old, inefficient technology, right? We take, what is this, 20, we take 20 atoms to get this nitrogen bonded to something. We end up throwing away 95% of the atoms that we start with. So that is and then that doesn't sound like much. They're atoms, they're tiny, right? But if I'm trying to make on an industrial scale, say I'm trying to make a ton of methylamine to sell, right? Academic labs like ours never use this much stuff. But the people who are making, the desk and the hardcover for your tablets and all that stuff, they're using tons and tons of this equipment. So if I try to make a ton of methylamine this way, I'm basically throwing away 19 tons of either this dicarboxylic acid or this thing. It's incredibly inefficient. Whereas here, if I use azide, I try to make a ton of methylamine, basically get, half a ton, a third of a ton of molecular nitrogen air. So it's a lot more efficient and clean. As you guys go through this, we don't talk about this a huge amount in undergraduate classes. And it's, and if you're not going to eventually be a chemist, probably you don't need to think about it. But as long as you think about, if you're thinking about any kind of environmental problem or industrial solution to something, anything you make, there's always going to be byproduct, there's going to be waste, and you have to deal with that. And in the lab, we maybe in your lab section, right, we fill up one little bucket, and it's oh, that's one little bucket. What does that do? But think about how many sections of organic lab there are. Think about how many colleges there are. It adds up. Yeah, I've got those memorized. Okay. What is the predict the product? All right. That's random molecules. Yeah, sure, let's do that. Like I said, your final exam is 9 days away. I love that. It just, the gas. I mean, you don't think about it, but I got, it means I got a writer file. Predict that problem. Hard. If you get the product, draw them like this. I've drawn the structure of triethylamine E3 and underneath it. Another 30 seconds. All right, so what's the strongest base in this? Triethylamine is the strongest base. Is there a decent acid base? Yeah. Now, I wouldn't say that's a decent, like the pKa, that's gonna be 19, 20. Like, that's not. So, well, okay, you could, that is the most acidic protein. So is that the most nucleophilic? You've got 2 nucleophilic atoms that you can think of. The triethylamine nitrogen is the strongest base. It's also nucleophilic. The ethyls, the reason we use triethylamine for so much of this, again, is industrial, right? We make a lot of ethyls. So I've talked about nature, and we didn't get to talk about fatty acid synthase, which I like. Nature basically takes acetic acids and polymerizes them to make fats, all right? So you take an acetic acid, you deprotonate the alpha carbon, it attacks another acetic acid ester. You end up with 4 carbons, you reduce one of the, you get a ketone, you reduce the ketone to an alcohol, you eliminate to an alkene, hydrogenate, now you've got a 4 carbon acid. You just do this over and over and over. So you find in nature, most biomolecules tend to have, we have way more even number of carbon molecules than we do. It ultimately comes from acetate. Obviously, humans like to make ethanol, right? And ethanol has then wound up both as recreation and sterilant. So back before we had the plethora of sterilizers we have now, we would use ethanol. You probably, I hope you've seen old enough movies, or maybe they do this in new movies where, you know, I don't mean to be, Mary was watching something the other day and had to cut some guy's leg off in the 18th century, and it's, you know, You get the patient really drunk, that's the anesthetic. The doctor takes a couple of swigs because this is gonna be hard. And then you sterilize where you're gonna saw with the booze. Like alcohol is actually an amazing product. So we make a lot of two carbon groups, acetic acid, ethanol. And so it ends up easy to put ethyls on the nitrogen and get triethylamine. So you'll see ethyls pop up kind of everywhere. You've also got a nucleophilic nitrogen here. And so even though you've got a decent base, triethylamine is not a strong enough base to deprotonate completely into alpha carbon. You've got a good nucleophile in the nitrogen. So anytime you guys see a nitrogen, you should be thinking, an amine, sorry, you should either be thinking base or nucleophile. So triethylamine is a much stronger base than acetic anhydride is an acid. So this is being run under basic conditions. And so the way this is going to start up, well, let me just draw the product. Might help. That was what I was asked, right? And if you want, you can indicate that you get this salt. Right, but the key thing is we're going to put an acetate group on the nitrogen. Right, this acetic anhydride, we make that from acetic acid. So we take acetic acid, we dehydrate it, we make that. So now we have a carbonyl with a good leaving group on it. So the way this reaction goes, the nitrogen is just going to attack. Triethylamine is going to take that acidic H. So the triethylamine does not take the NH2, one of the NH2 protons first. The NH2 proton is not acidic enough, right? The pKa of this is going to be like 30 or so. Triethylamine is not a strong enough base to take that. Here now, the pKa of an N plus, NH plus, more like 10. Kind of redrawn it there. Sorry about that. All right, and now that O minus, you've got a localized O minus, and it can kick out acetate, delocalized. So that's going to be favorable. And that gets you to your product. Bless you. So again, nucleophilic attack, proton transfer, elimination. As much as you can. I know I probably irritate you by saying, I tend to present it like it's easy. Like that is how an organic chemist thinks about mechanisms, modules. Here are the different steps I know. Can I put them together in some way that I get to the product? Right? That may not, you may put modules together and not get, and you may put modules together that get you to the product, and it turns out that's not the mechanism. In the lab, when this happens, like we discover some new reaction, we think about a mechanism, what we basically do is we think about all the different steps that might accomplish this. And we might come up with 2 or 3 overall mechanisms that would get us to the product. And then what we have to set about doing is doing experiments that rule some out. And sometimes you can't. Like, there are a lot of chemical reactions that we use all the time, both in a small scale lab and an industrial scale, that we don't honestly know the mechanism for. But we know it works. Yeah.
Does it matter if you like reform the renewable first and then do the deprotonation?
Yeah, so what she's asking, can just do this. And I'll try to draw this molecule 100 different ways. So the question is, does that matter? Does it go through there? And again, this is going to be one of those things where you'd have to be able to do some experiments to really rule this out. We have, and the proton transfer mostly takes place. Most of the reaction goes this way. Given that this is an aniline, right? This nitrogen, the lone pair in this molecule, on the nitrogen in the starting material, it's delocalized around that ring, right? So that nitrogen's not as strong a nucleophile or base. And so this is actually a much more acidic than you'd normally expect. The answer to your question is that is a pathway that can happen. The reason this structure is not as good as going this way is you wind up with a positively charged atom bonded to a carbonyl. Right, so this is not really an amide. Think about if I draw you guys an amide, and I say you're protein, like I give you an amide, acidic conditions. Look at this thing. And so if I give you draw the product. Promise I'm kind of answering your question. So your product, you should have protonated the carbonyl. That carbonyl oxygen is more basic than the nitrogen, both because carbonyl oxygen start out a little bit basic. They're not strong bases, but they're there. This nitrogen is actually pushing electron density toward the oxygen. The carbonyl, on the other hand, is pulling electron density away from the nitrogen. So this nitrogen is neither basic nor nucleophilic. And if you look at the product you get if you kick the acetate out first is a compound you'd get from protonating that nitrogen. And so what that means is, by the fact that I know that's not how you're getting to that thing, but the fact that when you protonate an amide, you protonate the O, means this is a higher energy intermediate. So going from here to there is farther uphill than going from here to there. So depending on the nitrogen, so the question you might be more interested in is if this is the mechanism on exam 3 or the final and you draw it that way, how many, if any, points do I take off? And I don't like to give it probably would receive a bit of a deduction. You wouldn't get nearly the deduction as you'd get if you had triethylamine pull that proton off first to make an N minus. Like it's a much more reasonable thing. And I guess that's, as if you encounter a mechanism that you don't know, I guess the point I've been trying to drive home. If you encounter a mechanism that you don't know, okay, and at this point, hopefully you've worked a bunch of mechanisms and you see some, and fate is in your favor on Wednesday. You actually see both the mechanisms. I give some away. Both the mechanisms on the test. Then I'm going to make you feel like you know something. But if you've seen them both, you just write them down, right? I know those. But if you have to work it out, what you want to do, think about the modular way we approach mechanism. And then just try to avoid any single step that is just clearly way uphill. So the one I keep saying is, what happens if triethylamine pulls this proton off first, right? If you look at what you get, and obviously if this was a mechanism, I will not ask you a question on an exam or a quiz like I just did in class, where it's give the product and the mechanism. If I'm going to ask you the mechanism, I'll give you the product. And if I ask you to predict the product, you don't have to show me a mechanism. So if you have this product, you know that one of these H's has to go away. Right? At some point, you have to have a base pull one of these H's off the nitrogen. You could do it here. you could do it there. You could also do it here, right? So you could. Do that. And this is really appealing. This always appeals to you guys being undergraduates I teach. Because if you pull that proton off, you're done. That's a great nucleophile. Then you would have this thing could just attack there. You get the tetrahedral intermediate, kick that down, take that out. You don't have to worry about pulling that H off again, all right? The problem is you also get this, right? So this has a pKa of about 10. This has a pKa of about 33. Like you're basically asking a reaction to go uphill 23 orders of magnitude. And that's just too far. Like I get that this sometimes where the bar is, like on this exam, we're doing aldols. And we have a bunch of aldols where the initial acid-base equilibrium is maybe 6 or 7 orders of magnitude uphill. But a reaction at the end drives it forward. 6 or 7 orders of magnitude when you have 10 to the 20th molecules. Okay. 23 orders of magnitude when you have maybe 10 to the 23rd molecules means you have 1 molecule. Right? That's just not enough to drive a reaction. And on this one, yeah. Okay.
The triethyl maybe you can't attack carbonyl.
Yeah, so the ethyls, I started into that whole ethyl thing and decided to tell you about amputations. My wife made me watch over the weekend. The other thing the ethyls do, in addition to being cheap, is they are sterically hindering that nitrogen, right? So you've got 3 ethyls sort of hanging around that lone pair. Makes that lone pair less nucleophilic. The other thing is there are no H's here. So if you get like that nitrogen can attack alpha carbon, can attack electrophiles. If it does, though, there's no H to lose here. Like if you look at all these mechanisms, the nitrogen attacks the carbonyl, we lose a proton, and then that nitrogen wants to stay. There's no way to make this nitrogen not be positive, which means it's going to be a decent leaving group. So when this tetrahedral intermediate goes to kick something out, that nitrogen is a good thing to kick out. Because you can't lose the H. Why doesn't the alpha carbon do anything in a reaction? So it is. Trying to think if I can tell you, because I don't want to give you a hard and fast rule, because like it will not surprise any of you. Alpha carbons are going to be nucleophiles on exam 2. And again, I'm not giving you anything. Most of chapter 21 is alpha carbons losing a proton and becoming nucleophilic. And so it comes down a little bit to, are there other good nucleophiles? Okay, so let's say this compound was not present. I just give you triethylamine and acetic anhydride. That's pretty much what you're left with. You're going to pull that proton off and it's going to attack something. And so there, triethylamine and the proton on an alpha carbon of acetic anhydride is going to have a pK of about 19 or 20. So it's like 10 orders of magnitude. It's not that far uphill. So you could get that. And then acetic acid or acetic anhydride could attack itself. Like the enolate of acetic anhydride would attack another unit of acetic anhydride. So what you have to look at there is that first step is quite a bit uphill. And you've got an amine with, like this amine is by itself a better nucleophile, or it's a really good nucleophile. And it's like it's, I'm trying to say, that thing, the white powder you dump into the reaction is a good nucleophile. To make this a good nucleophile, you have to have a very unfavorable acid-base reaction happen first. Does that make sense? So like a difficult thing has to happen first. Now, if I had said this is LDA and we do LDA and acetic anhydride first, and then we do this, LDA is gonna pull that proton off completely. We'd have the enolate. And then the enolate would do whatever it does with this compound. Another. And one from my right, the center. Anybody else? Actually, you asked me, sorry. We can come back to the.
I have a new question.
All right. No, new question sounds good.
Could you do this? This is.
This one?
Yeah, one, HCl.
Ooh, when did I do that?
Small, one.
It was young and had lived through a pandemic. Which somehow means I was meaner than her. This is it? That's all there is?
Yeah, that was it.
All right, predict that product. There's definitely a product. All right, now that you've worked on it for a second, what is mixing HCl and H2O do? So. H3O plus. Every time you see H3O plus, I don't know that I've said this to a number of you. Maybe I've said it in class. H3O plus is aqueous acid. Like if all I wrote there was H3O plus, I would actually mean there's water in there as well. You can't really have H3O plus without having water. The way we get H3O plus is we add some really strong mineral acid to water, HCl, sulfuric acid, nitric acid, HBr, something. All right, I'll give you another couple of minutes. All right, we talked about this one in a little bit on the Gabriel synthesis. H3O plus and water, heat, especially if there's heat there. So if you see acid and heat, you might think dehydration, right? If you have an alcohol, you're probably gonna do an elimination, you're gonna lose water. Take an alkene. If you see acid and heat and a carboxylic acid derivative, you should think hydrolysis. The other thing that would hydrolyze under these conditions would be an acetal, right? So we have we have two methyl esters. I don't say excess there, but that's probably gonna be it. Like H3O plus hydroxide, it's very rare to use that as like an equivalent of hydroxide or an equivalent of acid. So the first reasonable product that you guys could have drawn here could be incorrect. So, like, this is the 4-point question, and I see that, I probably give it a couple of depending on, I hate to admit that to you. Like everybody's acing the exam, and I'm like, oh, they're doing really well, I can be picky. That doesn't get me. If I get to that answer and I just like gave an average of 20% on the page before it, I'd probably get 3 of them. All right, so this is not the final answer. You probably should also write methanol. All right, methanol is, and I get this question a lot, and honestly, I don't, like if all you wrote here was methanol, it would be wrong. And if you wrote the correct product, but you didn't write methanol, I would probably give that full marks. And I don't know why that is, okay? Methanol is a small enough molecule, and if you ask me what the line is, I cannot tell you. I'm probably filling you full of confidence before exam 3. Going home, it's Thanksgiving, like the world is an inexact place. So just for safety at this point, write down, like if you hydrolyze an ester or an acid chloride or something like that, write that down. All right. That's not the final product, I said. What does this thing do when you heat it up? Do you have words to go with this? It breaks apart. It's not a hydrolysis. See people like telling their friends to say something. Nobody wants it. This is not, I would accept this. This is better than breaks apart. Like I understood this, but I know what it's supposed to do. So this decarboxylates. Yeah, it doesn't count if you didn't say it. So the way you view this, if you have a carbonyl and then really X here can be anything. If you have beta to that, a carboxylic acid, it needs to be the acid. Carbonyl in there. This thing will turn around and it will form an internal hydrogen bond like this, and then you get a Diels-Alder-like decarboxylation. So the mechanism is going to be that, right? You guys remember that Diels-Alder reaction, which you hopefully many of you learned again, relearned over the break. All right. So this gives us, if you follow these bonds, we make an OH bond, we get a carbon-carbon double bond, and we get a carbonyl. So this is going to be an enol and carbon dioxide. What really drives this reaction is the fact that the carbon dioxide is a gas and disappears, blows out the top of the reaction, right? You really can't put a condenser on there powerful enough to condense the carbon dioxide. Right? If I generate 100-degree carbon dioxide in my flask without pressurizing the thing or having a condenser that's basically at 4K, that carbon dioxide is going out of the top of your fume hood, out the stacks, and into the atmosphere. Congratulations, you just added to the problem. So the enol then, so again, if you drew methanol, carbon dioxide, and this enol, I would feel so bad for you. And I would probably still take a point. And here's why. You should know at this point that any carbonyl exists in equilibrium with an enol. So if the alpha carbon has an H on it, that carbonyl compound is going to have like 10 to the minus 12 phenol. Right? So if I have a mole of, let's say in this case, so X here would be, this is gonna be acetic acid, right? If I have acetic acid, if I have a mole of acetic acid, I have like a million enol molecules at any given moment, right? The keto-enol tautomerization is constant. Every molecule spends something like a 10 millionth of its life as the enol. And so if you find yourself getting to a product that's got a carbon-carbon double bond like this and an OH, odds are very good. What I'm looking for is the carbonyl compound that corresponds to that enol. So again, just for completeness sake, what I would want to see here would be these three products. The product that I got asked about, or the reaction I got asked about, a complete answer would be acetic acid, methanol, and CO2. That would be all the organic products. Incidentally, that may look like a weird problem to have on the exam. Typically, where this comes, right? This is part of that's part of the melodic ester synthesis. You can take a dicarbonyl compound. You can make the enolate with a relatively weak base. That enolate is a very good nucleophile. So you can alkylate it, and then you can hydrolyze it and decarboxylate it, and it's like alkylating the alpha carbon of a carboxylic acid. So that's part of you might see, if you see these dicarbonyl compounds, and the last step is H3O plus and heat, I'm probably looking for a decarboxylation. More questions? All right, I'm going to give you a problem. Yeah.
Dark trap. That was on a couple.
You didn't Google it? I bet it's got a good Wikipedia. I'm going to have to Google it. Dean Stark trap is a way of removing water. What was the reaction? Yeah, okay, let's talk about it. Yeah, okay. I didn't even ask. How was the bio exam? I'm great at marketing. She can walk off. I'm great at parties. Always asking awkward questions. I did a couple of weeks ago at a party, ask someone. My wife actually hit me on that. I asked how his wife was doing. They were divorced a year ago. I didn't follow on that. Like I was like, oh, it's recent. Like, no, you knew about this. We've talked about this. Like, I'm supposed to keep up with everybody. Good. All right. So the whole point of that is to try to like make you guys not think about chemistry for just a minute. Let me know if I get this wrong. Is there acid in this? BTAC. And this is the question. So she asked a question about the Dean Stark trap, and you guys have to do an entire problem. But it's a good one. I like this one. Predict that product, and then we'll talk about what the Dean Stark trap is.
So again, on these stepwise predictive products, take it one step at a time. Like, what is the product of step one? You don't explicitly have to tell me that, right? But the way to solve this problem is not to think, oh, what do all these three things do? Figure out what the product of step one is, and figure out what step two would do to that, and figure out what step three would do to that. All right, so product is step one. This is where we get our Dean Stark graph. It's going to be the imine. Plus, if you follow all the protons and stuff, water. All right, so the Dean Stark trap is a way to remove water. Imines will tend to form, especially if the imine is really conjugated. All right, this imine is not conjugated at all. So this carbon-nitrogen double bond is not conjugated to anything down here. There's an sp3 carbon between the nitrogen and the benzene. It's in a super stable imine, so you have to help it along. So the way we help, there are many ways. Like, I've kind of come down to just the Dean Stark trap's not that important. If you ever need to use it in the lab, it's just a piece of glassware you put in between the flask and the condenser. You can remove water with drying agent, right? We can put magnesium sulfate in, or molecular sieves. But what we do here is we're doing this reaction. I guess I didn't say Dean Stark trap. We're going to heat this up. We're going to boil it, and then it turns out, right? First, think about what the vapor will do. Vapor will come up here. It will just keep going. We'll heat this glassware up finally. The vapor will come over here, hit the condenser, but now we've moved the condenser off center. So now when stuff condenses, it falls down into this trap. Okay, so slowly solvent starts to pool in here. And the trick is benzene and water form an azeotrope. Right, so toluene and water form it. A lot of things form azeotropes with water. And so as water is produced in this step, in the reaction, it boils out with the solvent vapor. And at some point over here, you would have, shouldn't use this, we would have like, benzene, BHH, and then you'd have down at the bottom a little bit of water. It'd probably be cloudy, but the water that comes off, you can collect there. And on a big enough scale, where you get some accuracy, you can actually figure out when your reaction's done. Like, you can go in and calculate the theoretical yield of water, and you should collect that over here, right? Because benzene forms an azeotrope with water. That means they boil together, but they're not miscible with each other. So a Dean Stark trap, which I could have just said in 2 seconds. A Dean Stark trap is a way to remove water from a reaction. So it's a really elegant way to drive a reaction that is like making an acetal, making an amine, doing a dehydration. If I want to eliminate H2O to make an alkene, Dean Stark traps are nice. It's also just cool. It's cool. You can sit and watch this form. Yes.
Is that the final?
It is not. That is. Thank you for. Sometimes my head gets stuck. That is the product of step one. So what is step two? If you didn't get that as the product of step one, I'll give you a couple of minutes to think about what step two will do with that imine. So we've removed the water. There's no more water. Step two is taking this imine and methylpyrimine. Again, we'll finish up with that. It's a decently long one. All right, so the carbon nitrogen double bond is polarized. Nitrogen's more electronegative than carbon. So this works just like a graveyard with a carbonyl. And the overall process basically works like reductive amination, right? In a reductive amination, you make an amine, you have a hydride reducing agent. Lithium aluminum hydride, sodium borohydride, cyanoborohydride. Here, the reducing agent, instead of being an H, is a methyl. So the product of step 2 right, the nitrogen anion. So then step 3 is an acidic workup. And again, I would kind of accept either product here, like an acidic workup. You're adding acid to an amine. You're certainly going to protonate a negative nitrogen. And so I would sort of take either of these. So you might get NH. No, sorry, there's no H there. Sorry. Right, I would accept the neutral nitrogen, or if you wound up protonating it, and looking at the key that I had, I think I protonated the whole thing. Under acidic conditions, an amine is going to be protonated in general. So if you protonate it, that's fine. Everybody good with the deal, the Dean Stark trap? Right. I am probably going to check the wiki on that. I don't know. I have no idea who Dean and Stark are. So we've got acid in here. I have not yet done this mechanism for you. It's a good one to think about and practice proton transfers and what steps make sense. Amines are good enough nucleophiles to simply attack carbonyls. We saw that in the next panel over one of the earlier questions, right? An amine is a strong enough base, good enough nucleophile just to, as a neutral amine, attack the carbonyl. Given an acid catalyst, a lot of times you'll see people protonate these. Right, so if you protonate first, now this is a really reactive species, or the nitrogen could attack first. So I'm going to get us to the same place, then I'll talk about it a little bit. The key is under acidic conditions, right? Under acidic conditions, you want to try not to generate any really strong bases. All right. Well, the amine itself is basic, and so a lot of times you get asked, like if you do this reaction, if you use too much acid catalyst, you can kill the reaction because you just protonate your amine. And right, a protonated amine is not a good nucleophile. So that's going to be a catalytic amount of paratoluene sulfonic acid. I should have indicated that on the exam, which I didn't. The question she gave me. If you drew either of these routes to this molecule, I would accept it. And probably the even weirder thing than me accepting it is probably in solution, both routes happen a fair amount. All right, from here though, now we don't really have such a luxury. So now we're going to do a solvent-assisted proton transfer to move one of these H's over here. And in one respect, I've generated a base, right? That amine is the base. But once you get there, kicking water out gets us to the protonated amine. And again, depending on how much paratoluene sulfonic acid you put in there, that could actually be the product. I know I said the neutral is, right? We can't add methyl Grignard to this. Why can we not add methyl Grignard to this? What's the problem with that? So what happens if I take a solution of this compound, this protonated amine, and I add methyl Grignard, what happens? Right, the methyl anion just grabs this H and we're done. We get methane and we get D. Right, so Grignards always have to have enolates. If you make an enolate and then you want to do stuff with it, you can't have it be in equilibrium. You've got to make it and have it be dry. All right, so then probably the paratoluene sulfonic acid takes this off. I guess it's not that long. The fact that when we add nitrogen nucleophiles to ketones and aldehydes, does the nitrogen attack straight away, or do we have to protonate the carbonyl first? And again, either of those can happen. If you don't have an acid catalyst, right? So if this reaction had just said that, then it has to be this first, right? There's nothing to protonate that oxygen. We have to do this, and then a solvent-assisted proton transfer to get us over to here. The paratoluene sulfonic acid is really to get us to the water state. And like I said, it's really easy. If I use a full equivalent of paratoluene sulfonic acid, the amine reacts with the sulfonic acid, and we're done. So that proton's got to hop around kind of where you need it, which is a little counterintuitive given what I told you guys. Got 5 minutes left. Anybody got a quick one? All right. Like I said, I'll be in Salem 12 tomorrow night at 5:30. I will have some office hours tomorrow, but I have some stuff in town. I will get those posted tonight, what I'm doing, my office hours. One second. Then the review session tomorrow evening. I'll try to record that if I can. And then I will, and like I said, look for the email on instructions. If I don't hear from you, basically I'm expecting you to show up on Wednesday at 12:45 to take a 75-minute exam. But if you have an exam prior to that, or you're in my lab section, I'll give some relief. Right? So meaning, I don't mean like you'll get one less question or something. I mean, you'll take it started later. Please do the evaluation before the end of the week. Feel free to wait and see exam 3 before that if you want. And then, yeah, I'll see. If I don't see you Tuesday or in office hours, I'll see you on Wednesday. Get out of here. I should just learn how to end class. I'm having office hours right now. Right? I thought a lot of people would like to talk about their synthesis. Oh, crap. Hang on. You don't have to sit on again. There were some emails and I meant to put something together on this, and then Thanksgiving came. Your synthesis, right? All the carbons in your molecule have to come from benzene or ethanol. So you could do something like this, right? You could have, like, you could make that, and you could do something like, a lot of stuff to get down to, I don't know, something like this. Just as an example, and then you could put these two together to make your target. Right? I'm trying to be wild enough. You can use all the carbons in your final product have to come from ethanol or benzene. But like you could use 10 ethanols and 2 benzenes. Right? You just can't like, oh, I'm going to add cyanide, or oh, I'm going to add propionic anhydride or something like that.
If you can show me where you got, trace back every step, you can have 3 or 4 different lines going down and then put those products together to get to your final product. You don't have to just sort of have one chain all in a row. All right, now I'm done.